So we're going to learn a tiny bit about the nomenclature of organic compounds. Most of this we say for the second year of chemistry, organic chemistry. So the early chemists divided chemicals into two groups, organic and inorganic. Organic compounds are things that came from living organisms. Inorganic came from things that were not alive. And they found that the organic compounds were a lot easier to decompose, but harder to make, to synthesize. The inorganic compounds are harder to decompose, but they're easier to make in the lab. So today we know what the atoms are inside of these things, and so instead of saying, well, this came from a living organism, that one didn't, we define it by the content of the compound. And so organic compounds are composed of carbon and hydrogen, sometimes with some other elements present. Oxygen, nitrogen, phosphorus, sulfur, those are more common, but there can be traces of other things. But for organic compounds, what we're looking at is carbon and hydrogen. So the key element in organic chemistry is carbon. You may have heard on like these space travel shows and stuff, they talk about carbon-based life forms. Yeah, so the carbon atom, the element carbon, is the basis of most of the compounds in your body. So here is the smallest organic compound, methane, carbon with 4 hydrogens. Carbon makes covalent bonds exclusively, and when it bonds, it makes 4 covalent bonds. We'll learn later why that is, but for now, just believe me. Those could be single, double, or triple. A triple is 3 bonds, so you could have a triple bond and then 1 single bond, or you could have 2 double bonds, etc. And carbon can bond with itself or with other elements. And the chemistry of carbon is so unique and complicated because the carbon frequently bonds with other carbon atoms, making long chains of carbon atoms. And those chains can be straight, or they can have branches, they can make rings. There's all kinds of cool things. So here's an example of some compounds. This would be considered a straight chain because the carbons are just in a line. Here, the carbons have a branch. There's this line here, but then there's a branch off of that. So that's a branched compound. This is a ring. They're playing Ring Around the Rosie, right? The ones down here, here's one with a double bond, triple bond. Here the carbon's doing a double bond with oxygen, a single bond with an oxygen, and a single bond with a carbon. So lots of things possible. But carbon always makes 4 bonds. So these are categorized. Again, we like the flow charts. So we've got all the compounds, inorganic compounds, we talked about a bunch of those, and organic compounds. And then we can break these into groups, hydrocarbons and functionalized. Hydrocarbons have hydrogen and carbon. Hydrocarbons. So if it's just carbon and hydrogen, it's one of those. If it's fancier, it's called a functionalized hydrocarbon. Hydrocarbons compose common fuels. So oil, gasoline, liquid propane, natural gas, these are all hydrocarbons. They have high potential chemical energy. When you burn them, they release a lot of energy, so they're very useful as a fuel. We look at naming hydrocarbons by what kinds of bonds does the carbon have. Is it all single bonds? Are there any double bonds, any triple bonds? So the naming structure here is we have a base name, and the base name is determined by how many carbon atoms are there in the chain. And then there's a suffix that tells us if there's what kind of bonds there are. So we call these alkanes, the suffix is ane, alkenes, here the suffix is ene, and alkynes. So where does the base name that tells the number of carbons come from? Well, here's a table showing them. There probably should be something up here at the top of the table, but there isn't. Don't know why. So ignore the first four for now. Yeah, right. The pointer. There we go. Okay. Pent for 5, like pentagon. Hex, hept, oct, non, dec. These are the same prefixes we used earlier today without the A's at the end. Okay. And then the first 4, of course, have to be difficult. Meth, eth, prop, and bute. So how do you remember those? Mom eats pickled bananas. Oh, did you hear purple bananas? The one I learned was Mom eats pickled bananas. So you kind of wonder if moms may be expecting another child, right? MEPB. Meth, eth, prop, bute. 1, 2, 3, 4. I still say this in my head when I try to remember prop and bute because I get them mixed up all the time. Yeah.
You know, so before bananas become like bananas, the fruit that does like wrap up the bananas is purple.
Really?
Yeah.
Oh, that's cool. So he says before the bananas become bananas, the fruit before them is purple.
So
Cool.
It looks like a corn.
Like corn
With the bananas.
with little purple kernels on it, and those become the bananas?
Actually, like a wrapped corn. Like with the wrapped still on there.
Uh-huh.
Yeah. But then the inside is like the bananas.
Cool. That's very cool. I didn't know that. I learned 2 things today. I can't remember what the other one was, but I learned it. No. So then we take these prefixes and or base names, and we add these suffixes. So we can have methane, we could have propane, butane, or butene, or butine. So those are the, okay, this is a table of common hydrocarbons. So here we have methane, it's got 1 carbon. Propane has 3, Mom eats pickle bananas or purple. Butane has 4, pentane. Here's ethene. Okay, the ene tells me there's a double bond. So this has 2 carbons, and there's a double bond. There's only 2 carbons, so the double bond has to be between those 2 carbons. Now these names say nothing about the hydrogens, because what we do, like for propane, the prop part tells me it's 3. So I write 3 carbons. The ane tells me they're all single bonds. I know that the carbons have to have 4 bonds, and so I draw in the rest of those bonds and put hydrogens. Down here, this is ethine, 2 carbons. The ine tells me there's a triple bond. So then this one only has 2 hydrogens. Then there's a whole nother category, functionalized hydrocarbons. These have something different on them that adds a different function to the molecule, so they behave differently. You could argue that double bonds and triple bonds are functional groups, but so a group of compounds that have the same functional group is called a family. So methanol and isopropanol are both members of the alcohol family. And we're not going to learn how to name these, but meth you should recognize, oh, that's that prefix that means 1 carbon. And isopropanol, prop is the one that means 3 carbons. So this has 3 carbons in it, and this has 1 carbon in it. And what they have in common is they both have this OH functional group. And that is characteristic of an alcohol and causes the alcohols as a family to undergo very similar reactions. We can look at this as a family, and instead of writing out what this hydrocarbon group is, we can just call it R. And so R bonded to OH. And the R could be any hydrocarbon. The OH is the functional group that we're interested in. So this is showing some of the functional groups. So there's alcohols. The alcohol family has this OH functional group. Ether is characterized by an oxygen between two hydrocarbons. Aldehydes, there's a double bond with an oxygen. And ketones also, but one has a hydrogen on the carbon and one doesn't. Carboxylic acids are characterized by, it's kind of like a combination of a ketone and an alcohol. So there's a carbon with a double bond to an oxygen, and it also has an OH group. And it's the hydrogen on that OH group that is the acid part. That can leave and be an acid. So this is acetic acid. We've looked at that. Here it's drawn differently because we're showing its structural formula. So there's 2 carbons, there's 2 oxygens, and there's 4 hydrogens. There's 3 over here and 1 over there. This is the H that comes off, and the rest of it is the acetate. Esters have an added oxygen in there, and then there are amines. And amines have nitrogen. So these 3 highlighted ones are the ones I want you to be able to recognize. If it's got an OH in it, without anything else different, it's an alcohol. If it's got an OH with a double bonded oxygen nearby, it's a carboxylic acid. If it's got a nitrogen, it's an amine. Just kind of getting your feet wet for okay. Amine compounds tend not to smell very good. This one down here is the smell of rotten fish. Okay, so what should you be able to do? Well, draw the structural formula for nonane. What does that prefix non tell me? 9. 9 carbons. So in the absence of any other information, we're just going to put them in a line. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the math that we do in organic chemistry. It's a lot of counting of carbons. The ane suffix tells me that they are all single bonds. So then, what do? All of these carbons need 4 bonds. And so the extra bonds are going to be with hydrogen. Well, nonane is a hydrocarbon. It just has carbon and hydrogen. And the non prefix tells me the number of carbons, and the ane suffix tells me the types of bonds. They're all single bonds. So there aren't any double bonds or triple bonds with the carbons. And we've learned that carbon always makes 4 bonds. So, this carbon on the end has to have 3 more bonds. What are those going to be with? Hydrogen, the only other element in here. And it gets really tedious. And that's why we came up with lots of different shortcut ways for drawing something like this. So you don't have to write out hydrogen a gazillion times. Because it's a hydrocarbon and they're always carbon and hydrogens. Always carbon and hydrogen. It's the ane. The ane tells me it's a hydrocarbon with single bonds. If it was one of the things with a functional group, its name would be something else. And you don't have to draw any of those just the hydrocarbons. But we should be able to answer this next question: to which family does this compound belong? And what we're looking at is we're looking at this part. This is a carboxylic acid. Why? Well, because of this. Down here, this guy. I'm sorry, right here, this one. Carbon bond, double bonded to oxygen, and over here the OH. Now, I am not going to try to trick you by giving you an ester in there and, trying to get you to distinguish between them. No, the alcohols, the carboxylic acids, and the amines. The ones I highlighted earlier.